Good morning, chefs. I'm Mandi Walls, Technical Practice Manager at Chef. Today, it is my privilege to share with you some of the work we've been doing with policy-based provisioning, Chef support for containers, and making analytics data available on Enterprise Chef. Chef Metal is the code name of an exciting new feature for Chef. It lets you provision machines and turn them on or off according to policy. Policy-based provisioning makes a cluster of nodes as easy to manage as a single node. Chef Metal applies the principle of convergence. It exposes a new resource type called machine and allows you to include topology in your configuration policy. You use the machine resource to declare the nodes you want to create. Machine resources are idempotent. You specify your infrastructure in terms of policy and let it converge. Your policy can include nodes provisioned with different providers. You use whatever you need to meet your organization's computing requirements. You specify the policy, and the machine resource makes it happen. Right now, you may be using nice plugin commands to provision your nodes at the beginning of their lifecycle. The machine resource uses some of the same libraries as our plugins, so you'll find familiar settings when using machine resources. On this slide, we have two examples of the machine resource. Our recipe will create instances based on this policy. The machine resource names will be the node names when the instances are created in the cloud and in the Chef server. We specified recipes in the run lists of these nodes, just like you would with Knife. Because it's in a recipe, you can choose where the machine resource runs. In production, you might have the recipe run on a machine that contains you may run it on a special node called a provisioning node or a provisioning controller. When the provisioning node runs your Chef client, it brings your cluster closer to your desired state in terms of the number and kinds of nodes that run. This capability is very important in a variety of advanced scenarios, independent of the cloud provider you're working with. When you're in development, you could run the provisioning recipe on a Jenkins server to create nodes. I'm going to show you a provisioning scenario that uses a node in my network to act as the provisioner. I've given it the role Mario World Provisioner. Earlier, I ran the Chef client on my provisioning node and created two new nodes, Luigi 1 and Luigi 2. The new nodes were created. They joined my organization on the Chef server, and they have finalized their own configurations using roles and recipes that I specified in the machine resource. So let me show you how this looks. I'm going to go into my Luigi recipe that's part of the provisioning nodes run list. I'm going to change the number of Luigi nodes from 2 to 3 because I'm scaling up my application. I'll upload my change to the Chef server, and then I'm going to rerun Chef client on my provisioning node. Normally, I could just let this go. It would run on its periodic basis, and eventually the topology would converge to what I want. But we'll run it here in real time so we can see what it's doing. The instances I created earlier are already here, and they're up to date. You can see that Chef is reporting Luigi 1, Luigi 2. They're already good to go. When I get to Luigi 3, AWS builds me a third node. We didn't have to do anything to the other two boxes. They're already there and ready to go. So let me walk you through what's happening. We changed the number of Luigis from 2 to 3. We see a run instances request to our cloud provider. But we're only going to spin up one new node. The machine resource, because it's idempotent, we already have 2 of the 3 Luigis that we want. The new instance, Luigi 3, is created, downloads the recipes it needs to run from the Chef server. There's tremendous potential here. You can do so many things with the machine resource. The provisioning node might communicate with a Nagios monitoring server to determine when your cluster is running at high utilization. When that happens, the next run of Chef client on the provisioner increases the number of nodes for your web app, your storage cluster, anything else you can think of. Chef lets you provision the cluster using the same principles you use for configuring single nodes. The policy you use to control your infrastructure with Chef's machine resource is up to you. You have access to the entire database of knowledge about your network that's stored in the Chef server. You aren't limited to just a few performance counters that your cloud provider might monitor. Any policy you can come up with can be implemented. That's pretty fucking awesome, right? Like, yeah? Yeah. John Kaiser is going to tell you more about Chef Metal in his talk tomorrow. Now I'm going to show you some of the work we've been doing to support containers. Application containers are an OS feature that allows you to run your app in an isolated environment without the need for a separate kernel. They're kind of like mini VMs without all the resource overhead. Containers based on Linux's LXC library have been described as something between a cheroot on steroids and a full-fledged virtual machine. Container technology has been around in various forms for a number of years. As LXC has made its way into the mainline Linux kernel, working with containers and using them to create and run known good payloads has become easier and more common. An application can be effectively snapshotted in development and then deployed into testing and production without modification.
I have something for you.
I couldn't talk about containers without giving a shout out to our friends at Docker. Be sure to check out the Docker technical sessions later today and tomorrow. There's also a Docker BOF tomorrow at 3. And if you stay out too late after the party tonight, you can stop by the Docker recovery station tomorrow morning, and they'll be handing out supplies to help with that. So now we're going to run a demo that shows you how Chef can work with Docker to create container images. Creating images is super fast, but we want it to be part of a repeatable, predictable process, like all the other tasks we do in our infrastructure with Chef. We'll also create the images to create a cluster of MongoDB databases that are configured to work together, where all of the instances run inside of a container. Many companies, including Chef customers such as Intuit and Parse, use MongoDB to manage data in cases where a super flexible schema is needed. This is totally alpha, right? Sharing with you. For more information, though, track down Tom Duffield. He did a lot of the integration work on this. So this demo will show you how to use Chef at each stage of the Docker workflow. First, I'm going to create a Docker image using Chef. Then I'm going to use Chef Metal to provision and configure a host environment. After that, we'll use Chef to launch a few containers. Next, we'll use Chef to configure, monitor, and manage the new instances while they run. And finally, I'll show you a great new analytics feature that helps us keep an eye on everything. So we're going to show you how to build an industrial strength process for working with Docker. It's versionable, testable, and repeatable. Adding Chef lets you build a workflow that's ready for production and automated build environments. So we're using MongoDB for our example. It's an open source NoSQL document database. It's pretty common to have multiple MongoDB instances working together to form a database cluster. I'll use Chef to make an image from MongoDB that we'll later use to create a DB cluster running inside of containers. Even though I'm in dev mode right now, I want to make sure that I install MongoDB according to the best practices established for my organization. I'm just going to apply the standard Chef recipes for MongoDB that I've always used when I create the image. So in the Docker workflow, you can use a Docker file to specify which file system layers you want to use in your container. You might have an image that contains the base OS file system, and one or more layers that represent your environment. I'm going to use the new Chef machine resource that I showed you earlier. This code snippet shows how I've declared a machine resource that will create a Docker image. I could also spin up the resulting image, but for now, we're just going to create it. The create image action lets the machine resource know that it should just create this image and not leave the container running. So to do this, I've got some recipes set up that I'm just going to add to the run list of my provisioner. No pressure, I'm typing in front of all of you. I'm not Adam. Okay. There we go. You can see my provisioner has other stuff on it for the rest of my topology. Mario, Luigi, we talked about earlier, is still there. There's the output from my Luigi build. Okay. So we're going to go back through, check all of our recipes from earlier. All the recipes from earlier. Then we get into our topology. Mario, our Luigis. All right. While the image is baking, and this takes about 415 seconds, we'll talk about what's actually happening. We've added a new recipe to the provisioning node. We ran the Chef client on the provisioner. We used the machine resource to spin up a container on the provisioner with an Ubuntu image that we downloaded. The machine resource made sure to bootstrap the Chef client in our new container. We specified a special run list that told the new instance to install MongoDB and configure it. Finally, we take a snapshot of the container to create an image and put it on our Docker registry. Now, how do we run a container in a test or production environment? The first thing you need is a host to run the container. This is a physical or virtual node that's running Linux and also has Docker installed. There may be specific tunings required for machines that host containers, so we'd need to configure all of that as well. We'll use a machine resource for this. This code snippet shows how to declare an EC2 instance that has Docker in its run list. This makes sense because the node is going to host Docker containers. That will be its job. So we pre-baked this. And in my topology, I have a MongoDB box that I'm going to use as the host for these containers. Okay, and it has Docker in its recipe run list. Okay, in a lot of demos, you have to wait for the EC2 instance to spin up, but we are TV chefs, and we baked all these earlier. Looks like we're good, so let's take a look at what's actually happening here. The host for our containers has been set up and it's talking to the Chef server. I now have a host for the MongoDB container. It's up and running and tuned to the settings we want, so we can spin up some containers. Again, we've used the machine resource to describe our cluster. Here we specify that we want 2 containers running the MongoDB container image. We might do this, for example, in a test scenario when we want to check that our cluster logic is working correctly. So now we're going to add the launch recipe to this MongoDB host. Okay. All right. I'm on my MongoDB host, and I'm going to run Chef client. This host is going to run through its earlier recipes, and it's going to download the image from the Docker registry for our MongoDB. So you can see that second to last line there, where the image is going to come down and pull if missing. So we're going to fire up the 2 containers that we want. And this takes about 72 seconds. So you can have a drink and check out what DevOps Bob Ross is talking about this morning. We're almost there. Okay. It only feels like a long time when you're up here. Come on. Okay. There's my 2 containers running on the host that I've configured. We're ready to go. So what happened here? We run the Chef client. It caused the container host to use that new MongoDB image and instantiate 2 new containers. Sometimes you need to configure a container after it's been deployed. In this case, we need the MongoDB instances to query the Chef server to learn about other MongoDB nodes in their cluster. If they don't know each other's IP addresses, they can't act as a MongoDB cluster, and that would be very sad. So I want to point out a little detail on the machine resource that created the container. It contains a line that specifies the MongoDB replica set recipe as part of the run list. This means that when the container starts running, the Chef client has a chance to do its magic. Tuning applications or containers for a particular situation is typical in complex infrastructures. How do you share configuration data across a cluster of containers? How do you share that data resiliently, securely, easily, and quickly? You do this with Chef. All right. So now let's take a look at the actual configuration of this MongoDB cluster. And I'm timed out, to a host here. I'm going to SSH into one of the containers. Okay. Now I'm going to check out what Mongo's doing. Okay. And in here, I'm going to look at the configuration for the replica set. So these are 2 live instances that need to know about each other to share data and do awesome things. Okay. So the Chef client ran, configured these instances that are running in the containers. Part of the replica set recipe goes out to the Chef server, does a query to find all the other nodes of the replica set. Our containers are now updated with that information based on live infrastructure. We created a relationship between running containers that didn't exist when the image was created. So let's get a little more information about what we've got going today. To do that, I'm going to introduce another great new feature of Enterprise Chef called Chef Actions. Chef Actions give you insight into everything that happens to your Chef server, including cookbook updates and changes to nodes. I think you guys are going to love this. A lot of you have been asking for it, and I've talked to you about it, I know, a good while. So here's a diagram of how Chef Actions work. You can see that as events occur, the notifications are fed into an analytics pipeline. There's a variety of consumers of the notifications. For example, they can be written to a database that you can query at any time. So I'm going to open my web interface. There we go. Here's my analytics interface. And I'm actually going to query it for some information about that Luigi 3 node we were working on earlier. So here you can see what actions were taken, that acted on this particular object. Here I've got client provisioner created the stuff for Luigi 3 because I built that from my provisioner node with Chef Metal, right? So it's registering that that action was taken by a robot, really. Okay? I've also made changes to my MongoDB host. You can see that I did this action. There's me, and I made an update to MongoDB host. In the analytics pipeline, there's a couple of internal functions, and one of them is the ability to tag particular objects based on characteristics. This particular object, this MongoDB host, has Docker on it, and it's been tagged with the Docker tag. So I can use that to start filtering and working through all of the data that comes into my Chef server. So when I open up HipChat, I have a channel dedicated to receiving notifications from Chef actions. It shows me all of the actions on my Chef server, what organization they were in, who or what made the change, and what the change was. Very similar to what's in that analytics interface. Creates are green, updates are orange, and deletions are red. So here's what it looks like. Here's my creation of my Luigi 3s earlier in this demo, and some updates that we've done along the way. So let's create a data bag on the Chef server. I'm going to come into Chef Manage, Policy, Data Bags. Let's create a new one. Created my data bag. HipChat says, I just created a data bag, right? So that concludes our demo of new features. James Casey will be talking more about analytics tomorrow at 1:20. Don't forget the Chef Metal and Docker talks that we already mentioned. I hope you all enjoy ChefConf. I'll be here for the rest of the conference if you want to chat. Otherwise, have a fucking awesome time.